Yes. All right. Thank you all for coming. I know you had many options today, and I'm pleased to see so many of you here. I'm going to be talking about an open source hearing aid in Rust, something I've been working on for about a year and a half. Right. Where did I get this idea, or why did I decide to actually do this in the first place? My background is not in electrical engineering or embedded Rust or anything like that. I come from a finance background. I've spent the last 15 years working at investment banks, building pricing and financial modeling and stuff like that. So this is a far cry from sort of my background, but I've always been interested in electronics, and Arduino and stuff like that. And in fact, I got into the embedded space through the Arduino ecosystem. And I brought some props today. This is the first thing I ever made. This is like what I used to do. This is about 6 years ago or so. This is like an STM32 blue pill, and it's sort of cobbled together, and it's all wired up like this, and you put it on a breadboard. And this is kind of how I started my journey. And then I got into Rust in order to learn how to maybe make embedded software a little bit more professionally. I was introduced to Rust through and kind of Bluetooth at the same time. And I discovered over the pandemic, I started working on this thing called the LC3 codec, which is a Bluetooth audio codec. I kind of stumbled upon the spec when I was looking for stuff to do over the pandemic, and I looked at it and I thought, I don't understand anything there, but I'll give it a shot and see if I can implement the spec. And this is all about sort of audio compression for it's called low complexity audio compression. So it's for embedded devices. So this took me about a year to implement this thing because I didn't know what I was doing. It's kind of very similar to this project. No idea how to build a hearing aid in the first place. But this gave me confidence, and I figured I need to actually use this codec for something. I want to build something physical. Those are the things that I built before. I want to build something. I want to learn how to do PCB design. So that's kind of how I started in this whole area. Right, but before I start, I just want to explain what a hearing aid is. It's actually a very broad topic. A lot of people don't really know what a hearing aid is in general. So I asked our AI overlords to generate me an image of a hearing aid to show you guys, and it generated this creepy image over here. And it turns out it didn't know what a hearing aid was either, just that old people are supposed to wear them. Of course, that's not what a hearing aid really is, and hearing aids are meant to be worn by people from all walks of life. Part of what I'm excited about with this project is I want to bring hearing aids to a younger generation, and I want to make them less taboo to wear. So at its heart, hearing aid is essentially a microphone, some sort of form of amplification, and a speaker. So really simple, but it's all in the amplifier. What are you doing behind the scenes? And this is the kind of hearing aid that I'm going to be making over here. So this is called a receiver in the canal, and that thing over there is a little speaker that goes inside your canal, and then the rest of the hardware goes behind your ear. So battery, processor, microphone. Sometimes the microphone's in the ear, but that's actually quite rare for these kinds of hearing aids. So microphone's behind the ear. They're very discreet. They're often like the same color as your hair. And yeah, that's what I'm going to make. So while I was making this thing, I thought, this is not the only kind of hearing aid. You get behind the ear, which is like a tube. There's these big ones that you see. There's in the ear, which is kind of like molded to your ear. There's in the canal and invisible in the canal. And these are hearing aids that go right inside your canal, and you can't even see them. And those are, sort of way beyond my capabilities. I thought this is something that I can reasonably kind of make physically. And then there's body-worn hearing aids. So this idea to build an open source hearing aid is not a novel idea. There's a very popular project called Tympan, which I drew lots of inspiration from. It's quite a mature project. They use Arduino, and the hardware is actually quite. The hardware is so fast that they can run a lot. They can get away with doing lots of software-defined filters and stuff like that. So that's a really good project to look at if you're interested in the software-defined filtering and stuff like that. So anyway, I thought, well, what makes up a hearing aid, and at the bare minimum, what do I need to build in order to create something that's going to be reasonable to wear. Of course, when you look online at what a hearing aid does, you're just swamped by so much marketing material. It's hard to actually know at a technical level what it's really doing. So anyway, after lots of research, I kind of decided that if I implement these following 3 things, then at least I would have something like reasonable. Anyway, the first one, I'm sure you've all seen, is a graphics equalizer. This is something that breaks the frequency bands up, and then we've all done this. You make certain frequencies louder, and typically when you go to an audiologist, they will build you a little profile so that your hearing aid will change the frequency response. So that's easy. I can do that. I did very similar things with the LC3 codec. Then the next one was, this is a technology that I was very excited to learn about and to delve into. And this is the idea of audio compression. And this is not to be confused with like MP3 compression or zip file compression. This is what's called reducing the dynamic range of the audio. So this is very common in the music industry to make the singing voice more clear, to understand what people are saying, and it also has uses in hearing aids. So this is actually sort of a very simplified form of compression, but essentially at its heart, what compression does is it makes loud sounds quieter, and so that you can generally increase the volume of everything. So you can imagine a sound wave that's sort of bouncing all over the place. It's got huge peaks and troughs. You want to reduce the dynamic range and have everything in the same sort of energy band, and that's what compression really is. So here you can see this detects an attack, and then it sort of attenuates that, and it kind of brings it down. In hearing aids, it's a little bit more sophisticated than that. So you don't have a sound producer to sit there and vary the levels. You have to do that automatically. So if you're in a quiet room talking to people, it must generally bring up the sound. And if you're in a noisy environment, it must bring things down. And so it's just moving all the time on top of this whole attack release type stuff. And then another thing is noise gating technology, and that's if you're going to generally make things louder, then you're going to have hiss, microphone hiss, and all that sort of stuff. So you want to have sort of a noise. You want to get rid of that as well. And then the final thing that I needed to get working was ambient noise cancellation, and this is very critical to a hearing aid. This allows you to essentially a hearing aid. These particular hearing aids are they're very comfortable to wear. They're designed to be worn all day. They're invisible, but because of that, they don't push against your ear canal. They're ported. They breathe, and but they also let through sound. So you've got to subtract that audio through noise cancellation. And the other benefit of noise cancellation is it buys you time for adding latency to your audio pipeline. So you can imagine if you are taking a long time to process something, you would hear the process audio as an echo because it it would reach you at a later stage. So this is really exciting for me because this means that, stretched to its limits, you could possibly negate what somebody is saying and maybe even process the audio on a phone. Maybe you could do language translation, stuff like that. So this has got great potential, and I really need that. Okay. So without further ado, this is the device. I designed and got that thing made, and this whole talk is going to be about that process. And I happen to be wearing them, but it might be difficult to take them out because I've got this contraption on my head. But so hopefully you didn't notice that I was wearing them, and that was the whole point. But yeah, this is them over here, and that, yeah, you're not supposed to see it, and it's a very comfortable thing to wear. Didn't block my ears, which is why I could talk to you guys, which is really important as well. When you're wearing earphones, it's one of those things that's, it's a very antisocial thing to wear, but a hearing aid is a social thing. Okay, so there are a couple of things on this board. There are actually 61 components on this board. I won't go through all of them, but I'll discuss the ones that are most sort of interesting from a developer point of view. So you've got a microcontroller here and some other chips that I'll discuss later. This is the main chip that I've written software for. This is a dual-core microcontroller from Nordic. And I've got quite a lot of experience with working with this chip. It's quite a modern ARM Cortex M33. It runs at, one of the clocks runs at 128 megahertz. So one of the CPUs runs at that and the other one runs at 64. It's got a built-in Bluetooth radio, which is great, and it supports Bluetooth 5.3, I guess that's the latest version, or 5.4 maybe. But yeah, Nordic kind of leads the way in Bluetooth technology. So this uses Bluetooth Low Energy, which is great compared to Bluetooth Classic, which is not really feasible for hearing aids because it takes too much power. But Bluetooth Low Energy does work for hearing aids. Okay, so it wasn't enough for me to. My initial design, all I had was this chip, and then whatever I needed to power it. And this thing does a lot. You can do lots of software-defined filters on it, but you also need to sort of interact with the physical world, and you need to send audio. You need a thing called a digital to analog converter, and then an amplifier. And I couldn't find miniature versions of these things, and I tried to design my own. It was actually a real struggle, and I nearly put down the project as a result. I learned a lot about amplification and all that stuff, but at the end of the day, I realized that I didn't have the electronics skills to build something and be confident that I could make a low noise amplifier. So I really needed to find components that worked already, and not by chance, I discovered this DSP chip here by a company called Cirrus Logic. And I found it because I bought an audio dev kit from Nordic. And this is like, I've got a whole drawer full of dev kits. And this has been my sort of portal into this whole field. I rely on them to learn how the manufacturer wants you to use the chips and stuff. So a dev kit will come with schematics so that you can kind of see how you're supposed to power things and all that. So when I was looking through the schematic, I found that this little chip over there, you can hardly see it here. It's like a tiny little blip. That thing that's exactly what I want. It's got a amplifier and it's got a digital to analog converter, but it's so much more. And it's got a whole bunch of hardware accelerated stuff. This is just a few things that it can do, like multiply, accumulate, fast Fourier transforms, least mean squared, finite impulse response. These are things that, is a maths toolbox for doing audio compression or audio filters and stuff like that. Very, very, very useful. And then the last thing was battery charging. So this thing runs on a lithium-ion battery, and I had to find a way. That needs to be charged I didn't want to use disposable batteries. This the weird thing is, this is the simplest part of the whole system, but it's the only part that I didn't quite get right. And I can power the thing off batteries, and I can power it off USB, but the charging chip won't charge my chip, won't charge my battery for some reason. So it wasn't entirely a success, this whole thing. There's definitely more revisions to come out. But yeah, it was quite an emotional moment when these things arrived in February, and I plugged them in. They worked. They sat on my desk for a week. I just sat looking at them, and I was too scared to plug them in. Anyway, okay. So this talk is about this whole conference is about Rust. So I'm going to talk a little bit about embedded Rust and why on earth I would choose to make, when there's so much literature and there's so much stuff in C and C++, why would I build this in Rust? And yeah, your answer's over there. It's a safe language, and especially for memory safety, when you're dealing with audio, a large part of your memory is an audio buffer. So it's quite easy for, if you have memory problems or like a corrupted stack, for it to also corrupt your audio buffer. And hearing aids have pretty potent amplifiers on them, and you could actually do hearing damage. So here's like a safe language for a safe medical device. And just a little sort of segue here about ear damage. So people think that I'm a little bit crazy to be building a medical device, and I don't really, how can I do this? I'm going to damage my ears. But actually, this little speaker thing here, this is an off-the-shelf component. This is cool. This is like regarded as a consumable in the medical aid industry. People break these little wires all the time because you're manhandling them. So I basically chose this one because it fit. I could connect it to a board really easily. But I didn't know the tech specs for it, because they don't, it's all marketing mumbo jumbo. They don't ever give you that sort of information. So I kind of ordered a couple of these things, and by happy coincidence, the first one that I ordered did not impedance. It had a poor impedance match to my amplifier, which means that the energy from the amplifier kind of gets reflected when it hits the receiver. Now this is not what you want, obviously, in a device, but it also meant that if there was any mistakes in my code, or maybe there was some feedback or something like that, I wasn't going to blow my eardrums. So I've used this thing for my development, and then I have found RICs, wires that are impedance matched correctly. So yeah, that's a little sidetrack anecdote. Okay, so I decided to use a real-time operating system for this project, and I chose Embassy. And I've got experience with, I've used Embassy for quite a few years now, and it just keeps getting better and better. It's on stable Rust now. Embassy stands for async, embedded async, and it's just a runtime like Tokyo, but it's built for async. And this is regarded as a real-time operating system because it allows you to, and it's hardware accelerated. So the wakers are essentially connected to interrupts. So if you await something and you've set things up correctly, then your microcontroller actually can go to sleep for months at a time. So imagine a PC that can actually just sort of shut down when you await. It's like an amazing thing, and that's what you get when you're using Embassy. Of course, you have to do certain things the right way in order to achieve that. And I work with a power profiler, and I try out different things, and I see how much it's going to use, how much power each thing uses. So I'm just going to show you a little bit of example code that I wrote for this audio dev kit. So another thing was, once I started using this dev kit, this is great because I could start designing the program, and then I could also do the hardware at the same time. But I wrote it so that it could run on this thing and on the hearing aid. So this is a little program for this device, and this has got buttons and things, which is great. And all this little demo program does is, this is the play loop. This is running at 48 kilohertz, right? So this little loop is whistling around at, sub-millisecond latency here. And what this thing is doing is, if you happen to be pushing down, if it's in play state and you happen to be pushing down the tone button, it's going to fill the output buffer with samples from the waveform generator. If not, it's going to fill the output buffer with samples from the microphone. If I had to use callbacks and stuff like that, say I was using Arctic, a different, RTOS, I would have to somehow get this waveform generator onto that interrupt handler, and it would be maybe a little bit nasty. So this is a really easy way to sort of work with, this is how I would build stuff at a higher level. And this is why something like Embassy excites me so much, because it's so easy to do this stuff, and it's so readable. Here, this is the weight point over here, and this is because this is the full. Over here, at this point in time, we have the opportunity to run some software filters, so we can, do an FIR filter or whatever. And this is actually when I was experimenting with software filters, I would put all the logic here. I would do it all here. And because we're only dealing with 32 samples at a time, we have 650 microseconds of time to do our filter. It's not a lot of time, but we've only got 32 samples to work with. And then of course you could increase the number of samples, and then you get higher latency. So you want to keep your latency as low as possible. Otherwise you get echoes, and then active noise cancellation becomes a thing. Anyway, this send and receive is essentially, it's instructing the microprocessor, the microcontroller. It says, I've put the data in the right buffers. You can go to sleep now, and turn on a DMA, direct memory access peripheral, that essentially streams the audio to the peripheral. So that's been set up before. And if I look at the power profiler, the power drops, by 1,000 times while it's doing this, because it's done its high computation stuff, and now it's just sitting there streaming the data. And then if you happen to be in play state, I just wanted to show you this thing over here, and this is me using a bounded async channel of length 1. So this is regarded as quite a high-level thing to use on an embedded system, and the fact that you can even use async channels is amazing to me. So that's like a turnstile, and that just sits there and gates the thing, so that it just waits until another async task pushes the button. So obviously there are more tasks running on this thing that are off screen. Okay, a little bit about writing drivers. So the manufacturer of this DSP chip already supplied a driver, so why would I write the driver in Rust and do all that work again? But writing a driver is not actually such an intimidating thing. It's not a very complicated thing. I think when people think about writing drivers, they think of how difficult they are to write for operating systems like Windows and Linux and stuff. But writing drivers for embedded software is actually very straightforward. At the basic level, all you're really doing is you writing values to registers. And in this case, it's a 32-bit register, and there are a whole bunch of settings inside the register that essentially make up, they have side effects. So you write to this thing, and then there's a side effect of doing something. Right. So here's an example. Oh yes. When I was looking at the C libraries for this driver, typically it's like a large header file and listing all the registers, and then sort of a whole bunch of bit masks and bit shifting information. And once you know how it all works, it's kind of easy to use, but it doesn't actually get used that way. And even the sample code from the manufacturer didn't use their driver properly. I would see lots of hard-coded register values, and I say the manufacturer. These are example projects built by other teams. I don't want to blame anyone here, but I saw lots of sort of code duplication and sort of opaque things. So you'd write this register value, and then somewhere else in the code would write to the same register, but it was slightly different. And this is really difficult from a developer's point of view, because it's really hard to figure out what's going on, and you have to sometimes reverse engineer things, and I just didn't like that. And I thought there must be a better way to do this. And so this is kind of how you. I also wanted to make it so that you could still hard code things, and give people the benefit of the doubt. Maybe they're hard coding register values for performance reasons. You can pre-calculate it. Why do you have to calculate it on the fly? So here I wanted to make it so that you could hard code things, but you didn't have to. You could still read the code. So here I'm using something that's fairly recently stabilized in Rust, const expression, right? And this whole thing is a const function, which means that it gets evaluated at compile time. So this essentially just turns into a hard-coded two-dimensional array, which you can just blast down the line, SPI bus. So here's an example of an awesome example of zero-cost Rust at work, where you can actually see what you can. I'm forcing people to choose specific enums. There's no way to put invalid data in here, so it's really hard to mess this up, and anyone can look at this and understand what's going on. So here's a little excerpt from the data sheet, and this is a typical register. This is the dynamic range control. This is one of the control registers, and as you can see, this is jam-packed with lots of settings here. You can set the gain and thresholds and detection modes and quick release and all sorts of weird things. And here, this is the actual implementation of that information there. So it's not a lot of code. There's nothing fancy here. There's no macros. There's no unsafe Rust. And this is how you can write embedded software. In fact, there's no unsafe Rust in any of this code at all. Not that unsafe Rust is bad, but I just didn't need it because we're at the level now in Rust, in the Rust project, where these awesome tools are available to us. There's a little funny thing here where I'm allowing a U8 to be passed in, but I have to truncate it to 5 bits. So it would be nice for me to control that a little bit better. But yeah, at least you can't put invalid data in here. And the idea with these drivers is you're never really going to use a driver by itself. You're always going to reference the data sheet. You can build something on top of the driver so that you don't need to even look at the data sheet. But at this level, I wanted to make something that somebody could pair with the data sheet. And that's what this is. Right, that's the end of the Rust. I'm going to talk a little bit about how I went about building this thing. All the stuff is available on the repository, by the way. So you don't need to. Yeah, I specifically made this quite small because I just wanted to show you a brief sort of idea about how simple the circuit really is, and all that. So I used this EDM tool called KiCad, and I specifically use that because it's a free to use. It's open source. I could have used LTM Designer because they do have, free options for open source projects. But I kind of wanted something that was totally open source and free to use with no caveats. And then I also want to mention this YouTube channel here, Fool's Lab. I use so many resources online. I watch so many videos, and I'm indebted to so many people that just put their stuff up online. But I specifically wanted to sort of highlight this particular one because it was so sort of important for this task over here, and learning how to lay out a PCB, how to do the circuits, what things are important, what things aren't important, and all that sort of stuff. And he's got like a whole series of stuff. If you ever want to build your own PCB, then yeah, highly recommend that you look at that. Right. So just a little bit about how this works. There are actually 3 sheets on here. So this is a very simple circuit, a schematic. It's only like 4 pages, whereas this thing's got 30 pages, and this is a real beast. And that's, 30 pages isn't even that hardcore. Some things are, 100 pages, 200 pages. So you get, this is very straightforward. Because, and to me, it's kind of like Lego. I'm just connecting this microchip to that microchip using those wires. And you don't really need to have a very strong knowledge of electrical engineering to do this sort of stuff. You look at the data sheet and it tells you how to see all these capacitors and stuff here. These are essentially like local energy storage for power pins and stuff like that. And this is stuff that you learn when you're essentially building this stuff. And yeah, it was just a big learning process going through all this stuff. This is, once you've done the circuits, you start building you start routing it out like this, and there's certain techniques to that. And there's just a whole lot of stuff that I had to learn to do that. Okay, then getting it manufactured. So this is something that you don't learn when you're doing research, because this is an experience thing. So I'm quite excited to explain to you guys the thing that I went. When you watch these YouTubers, they're all sort of telling you these manufacturers are great because they're being sponsored by them, but nobody really tells you how the process actually goes. So I did lots of research, and I chose one of these 2 manufacturers, PCBware. If you've ever, these will be very familiar if you've ever looked into the space. JLC PCB or PCBware. These are based in China. And I won't say which one I actually ended up going with, because my experience probably had a lot to do with how naive I was, and I wouldn't be surprised if there's some serious technical problems with my design. So, it would be unfair to say, it didn't work because the manufacturer messed up. So just take the next few things with a grain of salt. So these guys both of them, I had dealings with both companies. They're extremely friendly. You have this sort of imposter syndrome when you're getting your first. This is my first PCB, by the way, to make. And you get this sort of imposter syndrome where you feel like you're wasting people's time if you don't really know what you're doing. And especially if you submit a design that you've never done before. But all the correspondence was so slick and so friendly, and the engineers got back to me, and the salespeople got back to me. In fact, it was so good that, and the English, the written English was so good that I actually assumed that I was speaking to a native English speaker, when in fact it was just a really good translation algorithm. So if I were to, and quite a few things got lost in translation, which caused delays. So I would say something, and then they would get a completely different thing, and it was because of the translation. So there's a little trick I use now. I write stuff in English, and then I convert it to Mandarin, and then I convert the Mandarin back to English, and then I read the 2 English versions, and if they kind of make sense, then at least I know, I'm not going to have fundamental problems there. So this is regarded as an advanced PCB. So this actually cost me quite a lot to make, about $1,100 to make 6 boards. They're tiny. So I was quite scared, submitting this thing, and I stared at this stuff for ages, and eventually I just pushed the button. I said, I'm just going to get it done. And if it blows up when I plug it in, so be it. But even that, the engineers did spot, they widened some of my tracks, and they fixed a few things for me. These guys X-ray things. This uses BGA parts, so ball grid array, and specifically the DSP chip. It's a 0.4 millimeter pitch pin, and the pins go throughout the whole chip, so you can't kind of root them out. So I needed to do what's called via in pad, so a hole in the pad, and this just increases the price of your stuff. So anyway, so not all these things worked. I had 6 made. I've kept one in its original packaging because I'm sentimental, and then these ones, I've got 2 that work, and these ones over here. This particular one was like a dead short, and I was missing a capacitor. This one, I couldn't communicate with the DSP chip at all, so it just didn't respond. So you kind of send a hello when you're communicating with these things, and this thing just didn't respond. This thing, it worked until I put it on my head, and my head started heating up the device, and then it started crackling. And then I figured out that it was just a dodgy solder joint, because when I push the chip down, it works. So definitely problems here, but I don't know if it's how I routed it or whether it really is a manufacturing defect. So that's why I said it's unfair to blame the manufacturer. But I think as this project goes, I'll speak to proper electrical engineers, and I'm sure they'll tell me what I did wrong. Okay, so that wasn't it. I still had to put this thing in an enclosure, right? And I had to learn how to make a 3D model and a parametric model. So parametric means that you can change various like angles and values, and you can elongate your model and stuff like that, so that I could experiment with different configurations. So that's kind of what it looks like over there. I used FreeCAD. I could have used an easier to use tool. This is actually an amazing tool once you get to learn it. It crashed a few times on me. And then like the other one, this Mango Jelly was a great resource to use. I learned so much from this chap. Here's my hearing aid kind of on the surgeon's table. I've got a little debug cable plugged into it there, so that's how I program it. There's the battery. It's a 40 milliamp hour battery. And then I've actually got off screen, I've got a power profiler on there. So I can actually see how much power I'm using. Then this is this is my 3D printer. I originally set up this in my office, but I moved it to an emergency workshop that I made in my spare toilet. So yeah, this hearing aid was made in the toilet, basically. This is a resin printer, and here's my sort of graveyard of past attempts. But it's the detail you get from these resin printers these days. This wasn't an expensive setup. This is about £500, and then I bought a little microscope there. But it wasn't a very expensive setup. So this is an accessible hobby, and you kind of have to have this setup. You can't really get a manufacturer to print these things for you, especially when you're iterating. So I might get a manufacturer to, once I have a solid design, maybe make something that's a bit more robust. But this resin is called nylon lac, and it's very tough. So I haven't had any durability problems with it. Okay, second last slide. So what are my plans for this project? First of all, I want to do sort of on the fly filtering. I want to be able to remotely control this hearing aid, so have like a command and control type setup, and be able to program it remotely as well. I want to have like an open API for Bluetooth, so that you can do control and logging. I want this thing to be used for research, but also for play. So I want people to buy this thing and maybe not even use it for a hearing aid. Maybe you can use it for, think about what a hearing aid really is. It's a socially acceptable thing to wear. It's not socially acceptable for you to sit there with headphones and talk to someone. But a hearing aid, you can do that. So you can have this form of mixed reality, and that's a really exciting thing for me. So you can is what people could potentially use this technology for. And right now, hearing aids are just used for hearing aids, and they're not used for anything else. So, I mean, I don't know if any of you have seen that movie, Her, where the guy talks to his AI companion. That's one of the things you can do. You know, you can have something that you talk to all the time. So this thing, because it's Bluetooth low energy, it can be streaming the audio to a phone, which can be processed. Maybe language translation. So imagine you're subtracting whatever the person's saying, and then it only plays the translated text to your ears. Like, imagine that. How amazing that would be. That would be sci-fi, you know? And then, like, stuff that's nothing to do with human communication, like maybe you want to do bird ID, or you want to bring the, you know, rumble of elephants that are subsonic, like, into the audible range, and so that you can, you know, hear elephants talking. I don't know, you know, what people want to use this thing for. And then the last but not least, people say, well, this project is doomed because how the hell are you going to make money from this? And I've actually taken a year out. I'm on a sabbatical, a year and a half, to do this project. So it's been a lot of work. And obviously, yeah, something like this is not sustainable. I can't just carry on doing this forever. So I thought, what are the ways in which this project could potentially make money? And that could be, and then I was thinking regulatory and medical certification. So these are very expensive things to do. Imagine this is a really popular project, but audiologists aren't using these things because they're not certified for use. So I envisaged maybe using the name of the project, but then having like a commercial arm that it has a certified thing. So I do have a plan. Whether it's feasible or not, I don't know yet. And that's it. That's it, guys. That's the code. It's the Matrix chat group. That's my email address.